Hello, my name is Adrian Freixas, and my teammates Abel, Freixas, and Andoni Acosta. We decided to build a half-full filtration system. One of the main problems in today's impoverished country is that people are drinking contaminated water. The main fact is because the lack of water in treatment facility and problem is sitting in this area, so they don't have another choice, and they tend to drink water that's contaminated. And this is what caused the deaths of 2,000 children per day globally, according to the UNICEF. These statistics come from the fact that the water that they drink is contaminated with pathogens that contains E. coli and bacteria such as Salmonella. And what they do is they call dysentery. Dysentery is just a medical term for diarrhea, and what it does is it dehydrates the body, compounding this issue. The best solution for this problem would be to implement some type of water treatment facility and plumbing system in this area, but that's next to impossible because we will mean to overhaul the society system. So the next solution is to find a way of purifying the water source. The way that we as engineers try to solve this issue is to try to build a system we could propel water to the self-filters. Our main motivation for this is that there is to give a chance to survival to these people, because there's a lot of wasted human potential to this issue. The goals for the system that we built was to have at least $1 per minute. It needed to be under a budget of $1,000, and it needed to be as simplistic and as robust as possible. I needed to have a lifelong experience. This is what other people have done so far to combat this issue. We have the lab shop. We just add tube inside with carbon filters inside of it. All you do is you suck through it. But the disadvantage of such a system is that you need to only drink at the water source, and it's impractical for the day-to-day use. Another system that I know people try to do was the solar bulb, which use solar energy to purify the water, but this system takes a lot of time, and it can only be used during the day. And the other system was the pure water bottle, that it uses a UV light at the bottom of the bottle to try to remove the bacteria, but it only does that. It doesn't remove the deposits from the water. Since we try to build our system around a set of filters, we need to choose what type of filters first we're going to be using. We looked into the membrane filters, we looked into the carbon filters, and we looked into the reverse osmosis filters. The membrane filters, they are at the top of the scale, but they need a lot of pressure in order to be used. The reverse osmosis, they tend to be complicated and expensive, and it does a really good job of removing salt from the water, but it's really expensive to operate. So we end up choosing the carbon filter, which is really cost-effective and removes 95% of the deposits of the water. But because you only remove the organic material, we decided to implement a UV light system just to remove the other side that was the bacteria. After we chose the system, we looked into what kind of pump we're going to be using. We looked into three main pumps. We looked into the boiler pump, we looked into the centrifugal pump, or we looked into the piston pump. We didn't go with the piston pump because the piston pump is expensive. It's kind of complicated. We looked into the centrifugal pump, even though it's around pressure ranges. It needs a lot of RPM in order to operate. Usually operate with an electric motor. So we chose to go with a boiler pump since it has a really low flow rate and is in operating RPMs. The standards that we use for this project, we went ahead and we abide by the ISO 9000 for manufacturing. We use to testing our water the APS standards, and for the electrical components of the cables and the alternator, we use the IEEE standards. Basically, this is the conceptual design of our system. As you can see, we have the storage tank, the pump strainer that basically is there to filter out any type of debris that might be harmful to our pump. The pump itself, we have also the gear system. The gear system is going to power the pump, and that's going to power an alternator, which in turn is going to charge a battery, which is going to power our UV light filtration system. We have an AC system. The reason why we decided to go to AC system instead of DC, because buying the DC system UV light is actually very expensive. It's actually cheaper buying an AC light filtration system, buying the converter, and buying the battery with the alternator than buying the DC system. Here we have the carbon filter. We use active carbon for the water. The reason why we chose it is because it's attracting negatively charged contaminants such as chloride and benzene. Also, we had to have the two carbon filter because we needed to provide for the UV light filtration system a clean body of water in order to operate a wall. This is the question that we use for calculation. The main question was the energy balance equation that we use in order to see what kind of pump we're going to use. We use it also in order to calculate the different pressure, the total head of the pump, and the power that the pump was going to have, that it required. These two equations right here, we use the bending. These are for the gear system itself. We use the bending equation for the bending factor of safety and the pin factor of safety. We also use these two formulas in order to calculate our life that our gear system was going to have. Using that equation with the stress cycle factor, we were able to calculate that the gear will have a life to 10 to the 8 cycles. This is how we chose our pump. This is the data from the manufacturer. We went ahead and we decided to make a gearbox in the 400 range of the RPM because we wanted to overshoot in case that we had any minor losses due to the fittings and the friction on the water. This is our system for a gearbox. It's a compound gear train, basically 1-to-4 gear ratio. You put an input of 100 and you get 400 out of it. Just that question that was used. This is the data for the alternator. We operate around 300 to 400 RPMs. It gives us around 200 watts. Our UV laser filtration system only takes around 10 watts. It's a big of an overkill, we were aware of that. But since we already had the alternator, we went ahead to implement it. But the upside about it is that if you want to charge something else besides the UV light filtration system, you could easily do it with the alternator. This is how it works. This is the UV light. This is the whole system, how it was packaged. That's the design of the gearbox. The gearbox is made out of PLA. The outside, the gears are steel. The shaft and the gears are made of steel. The brackets are made out of aluminum. And here you can see this is the input gear, and these two on the back are the output gear. One that goes, the blue one goes to a pump, and the one on the outside goes to the alternator. This is how it looks completely done. This is one of the things, one of the interesting aspect of the project. One of the big overhaul, one of the big hurdles that I think needed was how we were going to attach the gear to a shaft. We needed a way to attach it that would be simple and easy to take it apart if it was needed. The way that we decided is that we decided to buy the gears with a machinable hub. We tap and die the hub, so we created a thread so we can put a bolt in there. That's how it was. That's how we put the gears. So this is a little bit of how we operate the system. You turn on the UV light filtration system there, then you crank the gearbox. You can see the pressure, the outside pressure is going to start building up, and you can see clearly the water is going up. This is one of the tests, one of the first tests that we use for our system. Our biggest force was the static force of the gear system. Once you move out of the static friction, once you moved out of the gear, we moved very freely. So our biggest force was that. So we wanted to use that force in order to calculate the amount of power that is required for us to somebody to crank the handle. Also, we wanted to see the real RPM that our gears was giving out. How we did that is we did a system that had a laser, basically a receiving sensor, basically a photoresistor, that every time that the string would call the path of the laser, it would pick up an oscilloscope. We turned it into frequency. That's how we were able to calculate the RPM that the system was giving. And we found out that it was 93% efficiency.
Also, we wanted to run a certain test for the volumetric flow and the RPMs and pressure of our system. And for that, we implemented a series of tests based on filling up a gallon of water and timing, and then at the same time counting how many revolutions the person was given for that period of time. We came out with this chart which compares the pump data to our system, which is this line over here. And we found out that our operation point is around the 300 RPMs, which is good enough to provide 1 gallon per minute, which is our ultimate goal for the system. We also wanted to compare the volumetric flow with the handle RPM, the RPM that the person was giving the pump, to see how much effort that person had to do in order to provide the 1 gallon per minute. We found out it to be less than 100 revolution per minute, which is more than feasible for any regular person. We also wanted to compare the output flow with the differential pressure of the system, which is the total resistance that our system has, and is between 15 and 20 psi, which again goes with the flow that we want to get out of the system. After we did the physical test, we wanted to test chemically using the H2O water test kit in order to see if our filter, of course, filter the water or not. This kit is based on a few strips, color strips that you submerge in the water, and then you compare it to a table they have to see if they're within standards. This kit is EPA approved, so that's why we chose it to run a test. The first test that we did, of course, was of dirty water, and none of the factors passed the test. And we also, the test has 10 different factors. None of it was the dirty water pass. On the other hand, after we filter that water, we run it through the test, and we use the system, and then almost all of it passed. And then we tabulated this table so you guys can see, because it's hard to read out of the colors. Here is the dirty water. As you can see, none of the parameters passed, and most of them were out of range. On the other hand, our purified water, almost all of the parameters passed except the iron one, which we got 0.1 point, and we were supposed to get 0 part per million. We did extended research on it, and then we find out that this wasn't such a big of a hazard for the human body, for the health of the human. For the cost analysis, our system, our prototype cost $902. The final product, we will implement an aluminum casing, 2 sets of carbon filters, and a UV light. Such system will be able to purify 7,800 gallons based on the life expectancy of the pump. Based on the life expectancy of the pump. Keep in mind that with $1,097, you will be able to purify 7,800 gallons. If you were to buy that much purified water at $1.21 the gallon, the total will be $9,438, which, when you compare it to the system, is $8,438 just in saving for any organization that wants to aid not only countries in Africa but around the world. The purified water needs to be available. For visual works, as I mentioned before, we want to implement different materials for the casing. We also want to implement a smaller alternator and battery pack to keep our system as light as possible, to be semi-portable. And we want to design a packaging system to be shipped out around the world. This is how we design the time management for the whole project, for the whole year that we have with the project. And for the social responsibility, we design a system that is economically correct, meaning that anybody can operate, any adult, better say, can operate the system, and it wouldn't cause any harm, any physical harm to the person. It's cost effective for organizations, and it's usable around the world, anywhere that is needed. We after researching the cost of water around the world, we designed a system that is a sustainable purification system that can increase and aid opportunity for different organizations, and at the same time can reduce trash pollution from plastic bottled waters also.
Lifelong learning. One of the most important lessons that we learned throughout the project was the importance of brainstorming, how important it is to make all the changes during the design phase, because once you go into manufacturing and you make changes during manufacturing, it takes a lot of waste of resources and time. Also, we learn about teamwork skills, how important it is to know each other and to try to work as a team as well as possible. Organization skills, how important it is to keep on the project, which sometimes is kind of hard to do, and how to meet the deadline of the project. And global awareness, how important sometimes it is to look beyond our borders, because sometimes we live in a bubble, and because I was really shocked about the statistics that were shown in the previous slides. In conclusion, we were able to build a system that was able to at least have a 1 gallon per minute. We have a low cost compared to how much it costs to another countries, and we were able to have an environment, a better environment, and the testing result for a system proved that it's doable, it's feasible, it's not something that is impossible to do. Any questions?
Maybe a couple of questions. One, the pump, a lot of these places you're going to pick up all kinds of dirty water with sand and junk and rocks, all kinds of stuff you pick up. Is this pump capable of running that?
No, one of the disadvantages that this pump has, that's one of the main reasons why it shipped, is the cost, is that it is not good with abrasive materials. So one of the first things that we needed to do was we could have some kind of straining before the pump, at least I'd say 10 microns, the size of the straining. Because we know that if any dirt gets on the pump, it's going to be torn apart.
The second question is, you talked about longevity for the number of gallons, but carbon filter has a life too.
Yeah.
What are the carbon, because that might be in a third world country,
Yeah.
a hard thing to get hold of.
The carbon filter life is around 6,000 gallons of water. But the thing is that the carbon filter is very cheap. I mean, a good carbon filter is around $20 or $30, so which is not that much compared to a pump that is 150.
Yeah, I don't think cost is as much as availability in some of these backwoods. We're way out in the countryside, whether they would have it or not. But that's pretty good. If it lasts 6,000 gallons, that's really the life of your.
As you mentioned on the cost for the final, because this one a prototype, for the finals we included 2 set of filters and another UV light for the final cost of $1,097.
Okay.
Yeah, go ahead. The cost, do you guys, I can see the actual manufacturing cost. I don't know, I mean, because you have the components cost, but I don't know if there's a cost for manufacturing.
Oh no, that's the cost for the parts.
Okay. I mean, you take out because I mean someone has to put it together. And the other thing, I saw that when you were cranking the shaft, you had to put your hand on top of the black paint.
Yeah.
Have you guys considered something, maybe, I don't know, like a pedal? It's probably, and with your leg, probably have more stamina than with your arm.
Definitely, yeah. The maximum RPM that we were able to manage with this system was around 480. And after a minute of going at it, we were really exhausted. So
exactly. So
yeah.
and to put in some way that you don't have to actually put your hand and support yourself on top of instructor.
Why did you think that the maximum lifespan was only 7,800 gallons?
That's based on the manufacturer's for the pump.
And what is it about the pump that only allows it to survive for
The
7,800
materials.
gallons?
For this specific pump, we have 3 different materials. This one, which is the cheapest one, is made out of iron. We have an aluminum, I believe, and a stainless steel. Each of the other 2 increase the life span of the pump exponentially. The second one being double as this one, and the stainless steel is much higher. But we did a comparison with the iron one.
Right.
But we did look in
So I mean, huge savings, even higher savings,
we will
by
have even
the
higher
small
savings,
cost
yeah.
expenditure delta to put a stainless steel pump.
We basically compare our cheapest option. that's basically
But probably thinking about it now, probably if you add a pump that's gonna be a bang cost a little bit more, but it's gonna give you a better life expectancy, it could lower down the road the cost of electricity.
I also was interested that you used such a beefy alternator.
I know.
But thinking about it,
That's not
if you're in a third world nation,
Yeah, definitely.
that's probably easier to find that beefy
Yeah.
alternator than it is to
Yeah,
find one
and
you really
another
need.
thing is most of these people they don't have needed electricity, so they could definitely put a bulb to it and give power to a bulb to the gear system.
since we are outputting AC both power. These components didn't cost us anything. Alternator and the
What's the weight of
The weight around 80 pounds.
80 pounds?
Yeah, the battery is a huge weight when you consist.
So you need at least 2 people to carry it.
Yeah, definitely. As you see now, yeah.
You could see when we walk into the room.
Okay, thank you very much.